Okay, this little lesson is to prepare you for understanding the kinetic theory and what you're expected to know. So you are, for the AP exam, expected to understand the kinetic theory model of an ideal gas so that you can state the assumptions of the model and state the connection between the temperature and the mean translational kinetic energy and be able to apply it to calculate the mean speed of gas molecules as a function of their mass and their temperature. Okay, so let's take a look at the model and the specific assumptions within the model. Now, by the way, this model applies to, we're assuming that we're looking at matter that is made up of atoms or groups of connected atoms, which we call molecules. So if you can imagine matter in the three different states, we have solids, liquids, or gases. And in each of the different states of matter, they have different types of kinetic energy. For example, in solids, the molecules vibrate in more or less fixed centers. They're usually arranged in a crystal lattice formation, and you can see that they're moving back and forth, these atoms. So it's really a vibrational kinetic energy that we discuss in that case. In a liquid, the intermolecular distances between the different atoms and molecules they have a basically weaker intermolecular forces because they're further apart from one another. And so in this state, the molecules or the atoms have a lot more freedom of movement. So now we have a bit of rotational kinetic energy along with vibrational kinetic energy. And lastly, the state of gas, which is really what we're going to be looking for in this model. In a gas, the distance between the molecules is very, very large. And so there are very small attractive forces between the molecules because even though there are a lot of molecules, the average separation between the molecules is quite large. So here are the assumptions of the kinetic molecular theory model. First of all, the container has a, say, volume V. So this is a container with the gas molecules bouncing around in there. And there are a lot of molecules in that container, and their average separation between them is quite large. Now, when the molecules bounce around and collide with one another and collide with the walls of the container, they obey Newton's laws of motion. So F equals ma, a reaction force has an equal and opposite reaction force, so they obey all those things. Furthermore, when they undergo collisions, these collisions are elastic collisions. And remember, elastic collisions, momentum and kinetic energy is conserved. And of course, we mentioned earlier, the intermolecular forces between the molecules is negligible, except during a collision, of course. And lastly, we are assuming that all of these particles are identical to one another in mass, so it's a pure substance. In reality, when we talk about real gases, we have molecules of different types that have different sizes. The second big idea with the kinetic theory model of an ideal gas is that you are expected to understand the relationship between the temperature and the kinetic energy of the molecules. So according to the kinetic theory, there is a proof for this in your textbook shown on page 368. We know that the average translational kinetic energy of the molecules is directly proportional to the absolute temperature. Remember, that's the temperature in Kelvin. I'm not going to go through the specifics of the proof. You can look at your textbook and look at that. You're not expected to know the proof. What you are expected to know is the relationship and then being able to apply it to problems. So the formula that relates the average kinetic energy of the molecules in the gas is given by here, which I'm highlighting, 3/2 times a constant called Boltzmann constant times the temperature in Kelvin. This is the average kinetic energy for a single molecule. So, and now all the molecules are traveling at different random speeds. Some of them are going fast, some of them are going slow, and so we have to take a average kinetic energy here. If you're asked to find the total kinetic energy, or total translational kinetic energy to be specific with this, we would use the following formula. U equals 3/2 nRT. So we'll see that since we need to find all of the molecules, and we'll need to use the number of moles, N, then the universal constant, and then the temperature in Kelvin. Notice that there's nothing else besides moles and temperature that really affect the total amount of internal energy in a gas. Now, the other thing I want to point out with this too is this formula really only works for one type of molecule. It is a single molecule, what we call a monatomic gas. When you look at the other type of gases like diatomic gases, oxygen and nitrogen, O2, N2, then you have to deal with also a rotational kinetic energy. But even then, when we solve diatomic gases, we'll only be using the monatomic equation, and we'll be making the assumption. So all of the AP problems that we deal with is really just going to be limited to essentially monatomic gases. We'll just make that assumption. Alright, so if you want to find the total change in internal energy, really, hopefully you'll see that if you want to change the internal energy, you need to change the temperature. So the only way the internal energy of the gas is going to change is by increasing that temperature. Alright, the last piece of information that you need to understand is the connection between the mean speed of the gas molecules. Because you see that the kinetic energy is directly proportional to the temperature, and if you recall back before when we were studying kinetic energy, that's equal to 1/2 mv squared. But remember that the gas molecules are all traveling different speeds. Some are going really fast, some are going really slow. It's not just the straight arithmetic mean. It's actually a special type of mean. It's called the root mean square velocity. So we abbreviate this with a V and then a RMS, which RMS stands for root mean square. And what that means is that you see the kinetic energy is equal to 3/2 K, the constant, Boltzmann constant, times the temperature in Kelvin, and that kinetic energy is equal to 1/2 mass. If we assume all the molecules are identical in mass, we could just use m, and then this v, but this v is not the average but the root mean squared velocity. That's what's equal to 3/2 Boltzmann constant times temperature. So it's not actually the mean. So if I had like 5 different molecules traveling at different speeds, I wouldn't simply add all their velocities and divide by 5. The velocity we're looking at, which is directly related to this temperature in Kelvin, is actually taking all of the velocities, squaring them, adding them, and then dividing by the number of molecules, and then taking the root of all that. Hence, you could see you take the root of the mean, hence you're dividing by 5, and the square of all these means. So this is the velocity that's directly related to the temperature. Now if you rearrange this equation, you can see the halves cancel out here. You'll see that the VRMS is equal to 3 times the Boltzmann constant times the temperature divided by the mass, which is this formula right here that you can see. But instead of putting in m, that you would logically think probably would be the appropriate thing to put for the mass of the molecule, they decide on the AP formula sheet to use a mu. I don't know why, but that's what it is. So this is the mass of a single molecule written in kilograms. Now there is another way you can rewrite this, and this is in terms of the molecular mass. Remember we have the amount of atomic mass units, which is grams per mole. Well, if you know the atomic mass units, you can also find the molecular mass in kilograms per mole. So you can use this alternate equation if you know the molecular mass of the gas. This is what I call the microscopic version of the RMS velocity, because if you knew the mass of every single molecule, then you would use this formula. However, if you were given, say, oxygen or nitrogen gas, and you needed to, you knew that you could figure out the molar mass of that gas, then you could use this formula. To go from here to here, what we simply do is we know that the Boltzmann constant is really just the universal log gas constant divided by Avogadro's number. And when you substitute that in for here, on the bottom you'll have a massive molecule multiplied by Avogadro's number, which is the number of molecules per mole. And so what you end up with basically is a kilogram per mole, which is what we call the molecular mass. So another way you can rewrite this is this way as well. So you have this formula listed in the box here, which I've highlighted, and then also you have this formula over here highlighted in the box as well, and you are expected to determine mean speed of gas molecules as a function of their mass and temperature and solve problems like that. So I think you should now be ready to tackle on the next two problems.